Hello, folks. My name is Dan. For those of you who don't know me, welcome to the June edition of the Edmonton Python user group. If you want to find us on the web, you can go to EdmontonPy.com. If you want to find us on Twitter, you can go to EdmontonPy. And as well, always join us on the Slack, as there's always some great information there just about our meetups, some great discourse. If you want to get involved there. All of our meetups are recorded, as you can kind of see on YouTube, and it's on the Dev Edmonton. So all of our recordings are going to be shared on Dev Edmonton there. So hopefully you folks can join us there. All right. As usual, when we aren't in COVID, Startup Edmonton has and will most likely provide us a space to be able to host our meetup. So huge props to them on kind of continuing to give us space and support, as it's been, we never have to worry about it. So woo, claps, claps, claps. As well, if you folks want any more information, I'm sure that you folks probably have good sources. But here's a couple of good ones: alberta.ca/COVID-19, canada.ca/COVID-19. If you folks are also data geeks, there is a data export on the advanced kind of visualization that they are doing there. So if you want to play around with that data, that's available for you to play around with. All right. As well, since we have come on this topic with the protests that have been happening in recent weeks, there is some great reading here if you're interested in how race and technology are kind of together here. So we've got algorithms of oppression. So that's all about search engines and how they discriminate, which is pretty interesting. Race after technology, didn't get quite a deeper look at that. But Technicolor, race, technology, and everyday life, both of the rest of the ones are pretty interesting there. And artificial intelligence, how computers misunderstand the world. If you want to educate yourself and learn a little bit more about race and technology and how those two things are not necessarily equitable, or if you just want to educate yourself on the topic, that's something fantastic as well. And we'll be sharing this link, if we haven't already, in the EdmontonPy for that. All right. As well, there's some jobs out there. So for those of you who are thinking, hey, I need a new job, Sam Inc. is hiring a senior full stack developer. Meadow AI, they're doing some pretty cool stuff on hips, if I'm not correct. So they're looking for a machine learning engineer and a software dev intern. As well, if you folks are taking a look and want to make the move to more remote jobs, or you don't have the choice, there's a lot of cool sites here that you can go take a look at. So hnhiring.com. So that's a scraper on Hacker News, which is pretty cool. Remotepython.com. So all jobs that are remote with Python, that's a pretty cool one. And Remote OK. I think this was built by Peter Levels, which was actually pretty cool. He's on Indie Hackers, and I kind of follow him. So that's always something that's cool. And as well, we also have in our Slack channel, the opportunities channel in Slack, which is a great place to learn about jobs that are happening around town. So go take a look at those, and that's going to be a good time. All right. Events, the Python WebConf 2020 is happening June 17th to 19th. If you want to take a look at what they're going to be doing there, definitely go to that site. I think that PyOhio might be happening at the same time, but we didn't list it. That's my bad there. So again, this is probably a great place to see some great speakers discuss everything under the sun when it comes to Python. Right. So a couple things of news, mostly podcasts here. So Real Python episode 12. There's going to be some web scraping in Python, so tools, techniques, and legality, which is always something that you should be considering when you are scraping other people's websites. Podcast.init, they're talking about extending the life of Python 2 projects, as Python 2 is now officially out of support. So that's a pretty cool environment there. They get to talk all about it. Test and Code, they're talking with Nina Shakarenko. She has, I got to see her speak at PyCascades. She's a fantastic speaker and is always really interesting to listen to. And I think that she got on an episode of Django Chat, which is also a great podcast if you're interested. And Talk Python to me, 15 amazing PyTest plugins. If you want to simplify your testing, that's a great way. Or if you want to just learn a little bit more about PyTest and plugins and how it all works together, that's a great place to go take a look there. All right. As well, we do have some articles. So for those of you coming from different languages and you have used dependency injection in other languages, Python, it's a little bit different, a lot of the same ideas, but there's a great article there by Haki Benita if you want to go take a look at that. There's a practical Python programming course, which is really interesting. So if you're just kind of starting out or you want to get a little bit more familiar with it, that would be a fantastic way to kind of, I don't know, learn some more. 3.6 million data points, one GIF, visualize big data in Python. That was actually a really interesting article. So they're just talking about how to kind of compress everything into one nice looking GIF. That was actually pretty interesting there. Common Python security problems. I'm pretty sure that this was more web oriented, but at the same time, there's a lot of interesting pieces there. As I know, sometimes we treat security as this kind of like black magic, black box, but it's pretty interesting to learn about. And for those of you who are interested in kind of writing a little bit more asynchronous Python, you can take a look at the waiting in async IO. That's a really good one. The tour of Django server setups. I actually really like this article. It was a really nice way to kind of visualize the way that we can see different types of server setups. Sometimes you have a more rudimentary setup versus kind of having a load balancer and kind of separating everything. It was really nice to kind of get it drawn out. So that's something that is really nice. And as well, the last article there is keyword-only arguments in Python. So forcing your Python functions to only take keyword arguments or having certain arguments that are only keyword arguments. If you want to get a little bit more familiar with that, strongly suggest taking a look at it. That's really kind of like a neat little article there. Right. So moving on to the Python tip there. So we're talking a little bit about logging. And if you folks have worked in a production environment, having good logs is always a really good time. Having bad logs is how you get bald, like myself there. Yeah. So a couple of tips there. When we're kind of taking a look at it. So logger.exception includes the exception by default, which means that that first one, you don't need to include the exception. It's already going to be included in the second one there. So if you write logger.exception, just give kind of a meaningful message there so that you can have it there. And again, same thing with the third one. If you do something, it throws some type of exception. You don't need to pass the exception. You can just pass in, say, for example, the argument, which is actually kind of nice because you actually get a little bit more details. As well, just as a note there, the percent loggers are kind of like optimized to use percent strings, or I always forget what the name is for that. They're not formatted for F strings, and sometimes it does come out with some wonky stuff. So something to kind of take a look at. Yeah. So without further ado, as well, if you want to learn a little bit more about logging, these are a couple of links that you can click to learn all about it, just if you're curious. Okay, so today's talks, sorry, my apologies here. So today's talks are going to be an overview of machine learning hyperparameter search frameworks by Alex Wong. So I think that that's going to be a really fantastic talk. And Ryan has decided to give another awesome talk. So alpha, beta, Treesearch, and Python. So two really interesting talks today that we are going to take a look into. So again, before we kind of go on to these great talks, so we are possibly looking at July, but we are still struggling for speakers. Not struggling, we just need some more. So we are looking for presenters, and again, whatever you want to talk about is fantastic. And especially beginners, it's a great way to kind of get your name out there. It's a great way to put something on your resume, and it's a great way to give back into the community. If you come here all the time and you're thinking, I can't, I don't know, I just want to give back in some way. This is, again, a really fantastic way that really helps us organizers. And as well, any talk is welcome, whatever the topic. And to be honest with you, if you're thinking it's not complicated enough, those are the talks that are always really fantastic that I look forward to. Because you always learn some little detail, even if you're advanced. And it's a great way to kind of learn a lot more about the topic. If you can teach it, you can do it. It's great. All right. So I'm going to cue Aaron here, and I'm going to pass it off to Alex to talk about an overview of machine learning hyperparameter search framework. So,
hey. Okay. I'm presenting from my laptop right now, so I can't actually see if my screen is being shared, but I assume that it is. My name's Alex. I'm currently a master's student at the University of Alberta. I'm going to be giving my talk titled Hyperparameter Search Frameworks, an Overview. I also just shared a link to the slides on the YouTube public live chat, so if you want to skip ahead, you can do that as well. Okay, in machine learning, hyperparameters are the values used to control the learning algorithm and the training process. And this is different from the parameters within the neural network that does the actual inference. So this is a very simple input, hidden layer, output neural network. But when you're training this network, you have to worry about things like how many hidden layers do you want? How many units do you want per layer? What should my optimizer learning rate be? What optimizer should I use in general? And the list goes on and on and on. These are all the different knobs and dials that you can turn to change how the training of your model progresses. And it's really difficult to determine the values that you should use when you're training. And as an example, this is copy and pasted from the PyTorch ImageNet run file. So it's a standard argparse definition, and you need to specify what model architecture you want, the number of training data loader workers, how many epochs you want to train for, goes on and on. And this is a relatively simple example. For a lot of the new exotic architectures now, there's so many hyperparameters to choose from. So how do you do it? And the answer is use search. So optimize for an objective function, a numerical value that indicates desirability. What does that mean? It means that when I'm running my experiment, I want to output a single number that can tell me if my model is doing good or if my model is doing bad. So typically, this would be an accuracy on your validation or test set. It can be an F-score. It can be a loss. And it's usually very task dependent. Something that you don't have accuracy for example, would be to generate a realistic looking face. But then you can use loss or some other distance score to calculate your desirability function or result. So in general, there are 4 categories of these hyperparameter optimization algorithms. The first one is the most simple one, and it's exhaustive search. So these are things like hand tuning, grid search, random search. Hand tuning would be you know exactly what hyperparameters you want. You copy and pasted them straight from the academic research paper, and you're just going to modify it slightly in order to get it to run. Grid search would be taking the entire space of your hyperparameters and systematically searching every permutation until you've exhausted all of your combinations. And random search, it's throwing darts at the board with a blindfold. You're just randomly picking different configurations. You're running the experiment, you're logging the result, and then you repeat until you run out of credits on AWS. Evolutionary and heuristic search is the second broad category. This is where you have some initialization of your hyperparameters. You run your experiment. You select the best pool of experiments, and then you do some random mutations on these hyperparameters, and then you add them back into your population and you rerun your experiment. And the goal is over time, with enough of these evolutionary permutations, you'll get a pool of high-performing hyperparameters that you can use for training. The third step, or the third broad category, is known as Bayesian optimization. So the idea is that there is some function that goes from your hyperparameters to your, let's say, observed accuracy that you want to achieve. And if you can estimate a function that maps from these hyperparameters to your desired output, you can pick a maximum that will give you a max value that you want to achieve. And lastly, there are gradient and reinforcement-based learning techniques, or reinforcement learning-based techniques, where you estimate the gradient of your policy or your hyperparameters as they affect training. So I'm going to talk about some very popular Python hyperparameter search frameworks. If you click on this link, Control Tab, it will open up some comparison table that I've drawn out. These are 4 hyperparameter search frameworks that work with a whole slew of different deep learning frameworks like scikit-learn, PyTorch, TensorFlow. The one that I'm going to be focusing on is the one that has the most GitHub stars, and it's the one that I use most often, and it's Microsoft Neural Network Intelligence. And the reason why I like this one so much is because it is far more configurable and the documentation is a lot cleaner, in my opinion. The hyperparameter search algorithm that Optuna and Hydra uses is black box, and Deep only does genetic and evolutionary tuning. But for NNI, you can choose what tuning algorithm that you want to use, and there are many. Also, these 4 frameworks are not an exhaustive list. If you go to the Wikipedia page, there are so many, and they all do different types of tuning search methods. And there are frameworks that have tuning built into like model.fit. For instance, I know scikit-learn can do something like that. But it's harder to port that to something that's more generic, like if I had a custom PyTorch implementation that had a whole bunch of user-defined hyperparameters. All right, so this is the demo portion. I'm going to switch tab. All right, so I have created a really simple MNIST classification experiment. MNIST is the problem of taking black and white 28 by 28 images and classifying them into the digits 0 to 9. This is a simple conv1, conv2, fully connected linear layer, and then a classification layer that outputs 10 logits. And if you look at the parameters here, these are all the ones that can be configured. So using Microsoft's NNI, you define a experiment configuration where, this might be hard to see. I wonder if I can change this to light. There, maybe that's better. So this was taken from the NNI example directory. You specify how long you want all of your experiments to run, how many number of trials you want to run. If you have more resources, you can make it use remote distributed training. I believe you can hook NNI up with Kubernetes as well. And you tell it to run your Python file. And if you look at the search space, I'm saying, OK, I want my batch size to be either 16, 32, 64, or 128. I want my hidden size. So if you recall, going back to my code, hidden size is used here. I want my hidden size to be 128, 256, 512, 1024. Again, my learning rates should be one of these 4 values. And momentum, it can be a floating point value anywhere between 0 inclusive to 1 exclusive. So when I run my experiment, I've done this already because it takes about 40 minutes to run. When I run my experiment, I get this fancy web dashboard. So it tells you what your search space is. This is that JSON file that I've shown earlier. It gives you an overview of the config file. I wrote it in YAML, but here it is in JSON. And these are my 10 trials that I've run. One of the trials got 70.58 as my test accuracy. And most of them got over, 7 of them got over 99%. So let's take a look at the trials detail. And here you can see all the different trials, the different parameters that were used per trial. And there's this nice little chart that I like where you can see the different combinations of your hyperparameters and how they relate to your final metric that you're scoring for. So just at a glance right now, I can see that I probably don't want to use a learning rate that's too small because it doesn't seem to get a high test accuracy. Like if I go 0.0001, it's probably not large enough for me to train my experiment. But for things like hidden size, I can see that it doesn't really matter too much. Momentum, again, it doesn't really look like it matters. So a hyperparameter search framework can be really useful in determining parameter importance. There are additional tools that are built into NNI that can estimate parameter importance for you, but that is not covered in this dashboard. But the documentation is really nice, so I highly recommend just giving a read. Okay, so my closing remarks are that hyperparameters are very important. One thing that is lacking, but it's starting to come, is rather than just sharing your model architecture and saying that I have a really nifty recurrent neural network and it can classify, I don't know, a whole bunch of things in different sentences, it would be better to also share the hyperparameters so that other researchers, other scientists can replicate your work. This is one component of data science. So when people talk about an AutoML framework, they are lumping in everything, including cleaning your input training data, determining what features you want to use or constructing new features, what architecture family type that they want to use. All of that, in addition to hyperparameter search, is involved in end-to-end machine learning. And this last point here, run multiple times for stability. Just because you run an experiment with a set configuration of hyperparameters does not mean that your final score is the end-all be-all. You really need to run it multiple times to ensure that you have a statistically stable or sane result, which is why these hyperparameter search frameworks are useful, because you just set the configuration, you run, you leave it for a week, and then you can come back and see how everything has hashed out. All right, thank you. That's it for my talk. If there are any questions, I'll look at the YouTube chat. Yeah, so I like Eddie's comment about how he wishes he knew more about this doing his MSc. I've had my fair share of gross pudgy shell scripts and makefiles. And then I was, decided that I would move up and level up and have fancy web dashboards. How do you rule out the hyperparameters that you are tuning by looking at that dashboard? Good question. So I'm not using this to, maybe rule out is too strong of a word. Just looking at this fancy squiggly line, I want my lines to be connected to as high as possible. So in the top right corner, that says 100. I want my test accuracy to be as close to 100 as possible. So the lines that are not red, so this green line, this yellow line, this orange line, they all pass through 0.0001. So I'm not saying I'm ruling out a small learning rate, but I'm seeing that a learning rate that is too small does not get me a high test accuracy in this experiment. Yeah. So I think that's all the questions that I see in chat. Thank you for spending this time and listening to me talk.
Okay. All right, so our next talk is going to be alpha beta Treesearch in Python. So Ryan, whenever you're ready, I'll pull up your screen and I will get out of the way.
All right, one moment. I'm just going to share.
Yep.
All right.
Let's do that. And you're ready to go.
Cool. So I want to talk about alpha beta Treesearch. Treesearch is kind of the other half of machine intelligence that doesn't get talked about nearly as much as the machine learning, primarily because it's only really used in games, in game playing. But it's a really, really important part of game playing. When people talk about Stockfish or AlphaGo or any of these big game playing entities, they're always using some form of tree search along with the intelligence. And I wanted to talk about that because I've been building game players is a kind of a hobby of mine. A while back, I did another presentation on my Python game engine. I'm not going to talk about it here, but I am going to be using it a little bit. So I just wanted to just say, hey, I built a game engine. It's currently available via pip, current pip install Udebs. And it functions very similar to this guy right here. So we instantiate our instance and we can print the map. And then we basically give it these triples that say what action we're going to perform, and the map performs that action. And it can sort of hold the entire game state and make sure that people are following the rules without really very complicated code. But this isn't what I'm doing today. What I'm doing today is this. So this is a real URL. It's connected to a potato, so we could probably kill it by too many people going online. But effectively, I'm building generic game solvers and putting them on the internet. So hey, if you want to know how to win or solve positions in 4x4 Connect 4 or 4x4 tic-tac-toe and so on and so forth, it's here. And I wanted to talk to about okay, well, how do I go from being able to play a game to being able to actually show who wins in certain positions and what the best strategies are? And so that is what I actually want to talk about. And the answer is, how would one use Udebs to solve a game? The answer is, well, Treesearch, of course. So what is Treesearch? So I'm going to actually switch to code because if anyone has seen me present before, I always present with code because that's how I like to do things. And this right here is a basic tree search engine. So first I'm doing a substate of my game. So I'm just adding a bunch of methods to my game engine. And I have two methods, really, really simple. I have a legal moves method, which is telling me all of the moves that I'm allowed to make in this one position. Udebs itself will not accept illegal moves. That's part of it, but I still need to know what the legal ones are. And I have my actual tree search algorithm. Now, a tree search algorithm is a recursive algorithm. So recursive means it calls itself. So I'm going to, here's the result, and it's going to call itself here. And the recursive algorithm needs two fundamental components, and that is it needs to know when you've bottomed out, when there are no more children. And so Udebs handles that. And so when the game is over, it sets this self.value attribute to something. It's 0 if it's a tie, 1 or -1 if it's a win. But we're only going to take the negative value. So when it's over, whoever's turn it is to play has always lost, if that makes sense. So if you make a move and you win the game, then it's my turn, I've lost. So it's always going to return a negative value here. And secondly, each person, then we have an iterator that goes over all the different states, and then we have a choice function, a function here that makes a choice of all the children we want to descend into.
Hey, Ryan, sorry to just butt in here.
Yep.
Is it possible for you to zoom in a little bit on your screen by any chance? Perfect. Yeah, we just got a comment in chat there. Perfect.
That is, yes, I can definitely do that.
Okay, thank you.
So there's a couple other things I've got going on here. I've got a decorator on my result function. All this thing is doing is going to count how many times result gets called. So it's just a way, it's our main metric when we're working on this. Our main metric is actually how many times the function recurses. I'm less interested with how fast the function is and more interested in how many times it recurses. And we'll go over that in a little bit more detail in a bit. But so we're going to start on what's called 4x4 Connect 4, and we'll just run this V1. No, we're going to run the first one, so V0. Just kidding. If I were to try and run this, it would probably run for like days, if not months. And the reason is because the way we've kind of got this set up, I'm going to be running, doing an iteration over every permutation of every combination of every possible order that people could play these things, just 4x4 Connect 4. And so the point of Treesearch is, how can we make this more efficient? How can we not iterate over absolutely everything? So the first step is to add a basic hash function. So it's in Treesearch, so someone could play on the left here and then on the right, or we could have a different game where someone plays on the right first and then the left. They're the same move. So once we've solved one, we don't have to solve it again. So what we're going to do is we're going to implement a basic hash function here that just takes the state of position and transforms it into an immutable entity of some form, something we can stick in a dictionary. And then we're going to wrap this function and basically say, every time we come up with the same, every time we come to the same state, we don't have to recalculate it. And then finally, we actually have a function we can run. It's going to take about 30 seconds. So while that's going, so from here, where do we go from here? Well, the answer is we start adding knowledge about the game into the tree search. So in version 2, I'm going to make an observation and say, wait a minute, if someone plays here and then plays here, that's the same as someone playing here and then playing here. So we have symmetries in the game. And the symmetries mean that if we take the left-right mirror image of this board, we get the same board. I'm surprised this hasn't finished yet, but that's okay. So we get the same board. Well, I'm going to cancel this because clearly this is still too slow. So now we're going to add the symmetries. And hopefully that will complete faster. So great. All right. Now, but that's still very slow. We're talking about 4x4, and this thing is still just chugging along, not doing anything important. So, well, what other things do we know about the game that we can input it? Well, one thing is we're exhausting this list right here, and then we're choosing the biggest one. But the answer is, if this first one was a winning move, there we go. We finished in 28 seconds with 100,000 nodes searched. So in algorithms like this, you'll possibly see, like, let's say Stockfish, people saying, oh, it analyzes 100 million positions a second, or AlphaGo analyzes some amounts of positions a second. Well, basically what they're saying is they have an algorithm that looks like this, and they're taking this number or this number and dividing it by this number. So this is the amount of nodes we visited. We solved that in 188,000 nodes, and we did it in about 30 seconds. And so we're solving a lot of nodes per second, but we're not really doing it efficiently. So I just want to just point out here, when people say, I can solve 1 million nodes per second, that's not actually an indicator of how intelligent it is. Because I could have written this in a very efficient programming language, and it still would be not a good algorithm. So we're going to keep going. So once we have found a winning move, we don't have to look at the other ones. And the second thing I want to point out is, if the person above us has already found a tie move, then there's no point in us searching for a winning move, because they're not going to select the move that we've put in here. So if I know that the result function before this has already found a 0, then because I'm using this negative sign right here, I don't want to look for a 1, because then it's going to be a -1, and then they're not going to select that. They're going to select the 0. So that intuition comes out in an algorithm called alpha beta. So all I've switched here is this algorithm right here. This is the only thing that has switched. And so we're passing 2 parameters, alpha and beta, which is our minimum and maximum. We're still doing exactly the same here. We're still doing exactly the same here. We're iterating over it, and we're still calling the results. We're just doing this little check here to see if we have found a result better than the previous result. We're gonna return immediately. We're just gonna stop searching. And how much does that speed up our algorithm? A lot. So we've gone down from 100,000 nodes to 5,000 nodes. So a better algorithm doesn't just make this faster, it makes it so that we're searching less nodes. But we got more we can go from here. So in version 4, I forget what I call this one. No check. So there's another thing that we know, and the other thing that we know is that if my opponent has a winning move, so now we're going to start working on something called the heuristic. So I've modified the legal moves right here, And so in the previous one, this legal moves was just a very small function where we were starting from the left and working all the way to a right. But if we sort that in such a way that the moves that come out are more likely to be good, then we can reduce the number of nodes again. So I've implemented an algorithm here that just checks if it's a winning move. And if it's a winning move, we're only going to yield this one position. I don't care about any other move. If I'm going to win next turn, I don't care about playing in any other moves. And secondly, if my opponent has a winning move, I must play there because I don't want to play in a move that leaves me in check. So I call this the no check rule. It's like in chess, where you're not allowed to move while you're in check. Well, if the opponent is in check, if we're one move away from losing, we have to play there. And that gets us down to another 2,000 nodes. And at this point, we are going to go into our config file, and we're going to make the board bigger, because things get really, really fast, and it's really hard to see the improvements. Okay, this worked really, really well. And so in version 5, we're going to take that to the next level. We're going to completely solve the position. So first off, we're going to check if I win, and then instead of going into that node, we're just going to return the result to that node immediately, because what's the point in going into the node if I already know what happens? Likewise, I'm going to check if the forced win, and I'm also going to prune any moves that are above me. So if a person wins, I don't know if anyone has played Connect 4, but effectively, actually, I think I can just go here. Assuming this wasn't here, black doesn't want to, well, okay, that's a bad position, but there. So black doesn't want to play in this position because it would cause red to win immediately. So we can prune this node. Black should not play in here. And so that's what I'm going to do here. And likewise, I'm not going to move into the node, so I'm just going to return and want a -1 because everything's opposite. And so we can run that. So I'm just going to fully solve the position. On a bigger map. Actually, I should have done that on a smaller one so that we can have a point of comparison. All right, so that one's going to give us 4,000. And version 3 was, oh no, that was version 5. So that's version 3. No, never mind. Version 4. All right, well, I have a, yep. So that improvement apparently didn't work. I thought I checked this. All right, well, whatever. Moving forward. Yeah, okay. Oh, no, that was version 4 to version 5. Okay, yes, so I fully solved the position. We're going to go version 3. Yeah, so from version 3 to version 4. Oh, never mind. Okay. All right, let's just skip that and go straight to version 6. Okay, by this point, I'm going to start adding a heuristic. So I've fully solved the position, so let's just, yeah, something wrong with that. I fully solved this position, and I'm going to add a heuristic finally. So once I've done all this full solution, I'm going to sort my algorithms from the middle out to the edges. That will improve the thing, but I just wanted to point this one out because could someone add a machine learning algorithm here? And the answer is absolutely yes. You could throw a machine learning algorithm here that would then sort your possible moves by most likely to be good from most likely to be bad. And all right, now we're solving 5, but we've gotten bigger. So now we're solving 5 by 4. And this goes on and this goes on. So I can build a customized cache object that takes better advantage of the cache, or I can optimize, or I can build a strong solver. This is about as far as I want to go, but it's a good example of what I mean by how you actually do this. The best I've gotten so far V9 strong solver is solving the 5x3 in about 2 seconds. So unfortunately, that's still not that great. So where do we go from here? Well, 2 major points of improvement. Faster code. A C++ version of this algorithm exists. I've been actually following someone else's tutorial and porting it to Python, but it doesn't really fit Python because it's really low level. But it runs about 1,000 times faster than what my current algorithm is doing. And it solves Connect 4, 6x7, 7x6 in reasonable amount of time. Stockfish, which is a chess engine, uses alpha beta search with really, really powerful heuristics. And it analyzes about 70 million positions per second, and it is superhuman. It plays better than, way better than the best human players. However, faster code and being able to analyze more positions per second has its limits. No matter how much you optimize, things grow linearly and game complexity increases exponentially. We noticed when switching from the 4x4 to the 5x4, we went from like half a second to 30 seconds. And if we switch to the 5x5, it increases like that again. So where do we go from here? Better algorithm. It's always about the better algorithm. AlphaZero, which is another chess playing engine, analyzes only about 40,000 positions per second to Stockfish's 70 million. It uses a neural network as a heuristic, and not many people, they keep talking about, oh, neural network solved it, but it uses a Treesearch algorithm, and it uses the neural network to sort the nodes of the Treesearch that it's looking for. It doesn't use alpha beta, though. It uses a different one called Monte Carlo Treesearch, and it regularly beats Stockfish. Stockfish doesn't really have a hope against this thing. So yeah, smarter code is better than faster code, and that's kind of all I have. So, any questions?
Yeah, I think we have a question here from Alex. He's asking if your experiments are open source.
So the engine itself is. The experiments are. I generally post everything I'm doing in GitHub, but I won't be publishing them with the engine. The engine is just something completely different.
Okay.
And one thing I did want to get out of this is because I've got that version 1, version 2, and I clearly got some work to do on it because there's some breaks in the improvement, but I wanted to actually talk through all the various improvements. So I do plan on putting up a full tutorial that actually talks through each version of the code. It is not available right now. So okay. That is not available. But the engine itself is that I use to do my game analysis. I'm still I'm always optimizing this thing to get it going faster and faster. Unfortunately, the C++ version literally runs 1,000 times faster. And that is kind of a big handicap that I'm working with. Right, yeah. Okay. So yeah, that's it. Okay, sounds good. I think we have next questions from Dan here. He's asking, how/where would you tie in reinforcement learning with alpha beta tree search, with the caveat this might be a loaded question? Oh no, that's actually I one of the reasons I did this is because I was trying to figure that out. Like, how does these two algorithms work together? And the answer is alpha beta tree search is not used in the training. So basically what happens is they have a playing algorithm and a training algorithm. And basically the playing algorithm plays itself and creates training data. Basically says, in this position, I won. In this position, I lost. In this position, I won. And they basically train an algorithm that tries to estimate the probability of winning a certain position. So X has a 30% probability of winning this position. Y has a 10% probability of winning this position. And then basically what they do is then that goes into the playing engine, and then they use that to sort the moves. So every time it goes into a node, it grabs all the moves, it applies a it applies it applies the neural network on all the moves, sorts them in most likely to succeed to least likely to succeed, and then descends down the most likely to succeed first cases all too often. The thing is the you can kind of think about it like the neural network is the intuition, while the alpha beta search is the analysis.
Okay.
And so alpha, like Monte Carlo and AlphaZero actually proves itself wrong a lot, where it doesn't go with its best intuition move or the best move the neural network said that. But the sorting allows it to solve in 40K positions what a better solution than Stockfish can do in 70 million.
I see. Okay. Excellent.
So,
Alrighty. Perfect. Okay, I think, let's see here. We just got a comment from Daniel Joe. Really like the iterative approach to the subject. He remembered some stuff from Alpha Beta from a course. Looking back, he would have loved to build up from where he kind of left off. So once again, thanks for doing this talk.
No, I like the iterative, and Treesearch can be some of the hardest things to debug. So keeping your old versions to compare them against is absolutely necessary.
That's true.
Because it's really, really hard to debug.
Yeah, I could totally see that. But it's also good too to have these checkpoints along the way so that you can empirically tell, are these making improvements?
Are they not?
Or are they not? Yeah. Cool.
Yeah.
Okay. Well, thanks again, Ryan. I'm going to now add Dan, who will just kind of close off the stream for us now.
Yeah, folks, a couple really awesome presentations, especially for me personally. I was super excited about those. So thanks again to Alex and Ryan for giving some talks where now I'm pretty giddy about alpha beta tree search and tuning hyperparameters, which is a couple things that I'm looking into myself. So some pretty cool things. So again, folks, Alex and Ryan have been awesome this month in giving us a really some great talks. And again, these and I don't think that I'm speaking for not necessarily all of us here, but those are some pretty advanced topics which are pretty great. But again, if you want to present and it's your first time, you don't necessarily need to have a talking about machine learning or talking about that. You could just talk about the fundamentals of Python, as I know that if you're listening to me say this and you're thinking, that would be really awesome to have. It would be really awesome if you folks just tried to kind of give it for a whirl, and sometimes you figure out that you really like it. So it's a really good time. So we're not completely sure whether or not, depending if we do have speakers or not, if we're going to have a July meetup. If it is going to be the second Monday in July, which is going to be July 13th. So you could definitely catch us there. And hopefully Ryan and Alex, I'm pretty sure that they've shared all of their information on, and it's going to be on the Slack. So Ryan and Alex, if I could humbly ask if you could share some of that info on Slack, that would be really great. And besides that, folks, thank you so much for coming out. Hopefully we'll be together soon, and hopefully you are all holding up all right. And
100%.
Yeah, hopefully we'll see you July 13th. Yes, what's up?
Could you share your screen again? How will anyone with any ideas of how to speak, how are they going to reach out to us?
Yes,
slide there with all of our Slack usernames.
That is actually perfect. So I did a really silly thing in actually not stopping to share my screen.
That's okay. Yeah, while you're finding that out, I will be updating this. So this YouTube stream, once it ends, it will become a YouTube video. And once that happens, we will be able to Alex's slides to the video description. So,
yeah. So as well, folks,
there we go.
if you folks are interested in speaking, please send us a message on Slack. You can send a message at Aaron Young, at Asha, at DataGet, or at DG Morris, which is myself. So that's a great way to get in contact with us. And again, join the Dev Edmonton Slack. If you haven't already, just go to devedmonton.com. I think that's right. And join the Slack at the bottom. Right here, you just click this button and you're ready to go to be able to join us. And if you haven't seen it before, again, hopefully I'm not going to be sharing anything too sensitive here. I'll just go to the Meetup EdmontonPy, so you could just go explore it. So here, EdmontonPy. So all of us are on here. And again, it would be a really fantastic way to get to know you folks. And yeah, so please join. And hopefully we'll see you July 13th. I think that's pretty much it.
Awesome. Okay. Thanks, everyone. Have a good night.
See ya.